I want to say a little bit more about cosine and the quadratic approximation and the error bound for that. I promised a computer picture, and I want to make a little more explicit the fact that it's a particularly good estimate, and that'll tie in nicely with the next thing we'll do with higher order Taylor polynomials. So we've got cosine of x as our function, a equals 0 here, because that's a very natural value and it's also convenient. And so the quadratic approximation is very simple, 1 minus x squared over 2. We've got this remainder estimate. I'm going to use the 1/12th version. That's the version that's the best we could easily get when x was allowed to vary anywhere between minus pi over 6 and pi over 6. And if you look at the graph, I'm going to switch over to the computer plot here. So here the bold, of course, is the thick line is of course cosine. The thin but solid line is the quadratic approximation, and the dotted lines here are the worst case scenarios. That would be what if you take the upper one here on the right, it's the wiggly thing on the right, and then it actually becomes the lower one on the left. That is when you add in the cubic term, the 1/12th x cubed. So and then the lower one on the right actually syncs up with the upper one on the left. Those are those two cubics. That's if you subtract off 1/12th x cubed. And so those are the bounds. If we erased the bold line and had no idea what cosine actually looked like, we would say that our approximation is that it should be somewhere near this thin solid line, this quadratic, 1 minus x squared over 2. But as far as we know, all we know is it's between these two dotted lines over here, and it's between these two dotted lines or curves over here. Now you can see those get pretty close together, and when x is less than about a half, it's hard to see the difference. Well, I've zoomed in. Okay. And so once again, now here where x is less than 1, and especially maybe look at the middle part of the graph, it's even on this scale, it's still hard to tell the difference between all of these graphs. They seem to join at about x equals 0.4. But notice that when you actually put in the graph of cosine, that's again the solid line, the thick line, the graph of 1 minus x squared over 2 is really quite close to the real thing, way closer than these rather conservative error bounds would suggest. So let's look at just one numerical example, and then we'll go back to going to higher degree polynomials, higher order approximations, and we'll see if there's an explanation for that. So I've just written it down here. I picked like 0.2 as a value that's not super tiny. When it's super tiny, we do expect it to be really good, but is definitely less than pi over 6. The cosine itself from the calculator is 0.9800666 approximately. And one question you might have is, hey, what is that? How does the calculator know? And we'll get to that. Our approximation is 0.98, and notice those two zeros in there. That's giving us the fact that the remainder is 0.0000666 about, very close to 2/3 times 10 to the minus 4th. Well, if you calculate our error bound, 1/12 times 0.2 cubed, turns out to be 2/3 times 10 to the minus 3. So the actual remainder is 10 times better, 1/10 of what our error bound is guaranteeing for this particular example. So it's certainly nice to know. If you just needed, say 3 decimal places of accuracy, it's great to know that it would be sufficient to just say, look, for sure, without a calculator, I know this is true, so I get those 3 decimal places. But it's interesting that you get basically 1 more decimal place than you expected. So let's look into what a higher order approximation to cosine would be. I don't want to say cosine is the only example, but it's just such a nice example to work with. So we still got f of x equals cosine x. Let's again write out the derivatives. Minus sine x. Hopefully this isn't too tedious to see this over and over again. But we're going to notice something very interesting. At the 4th derivative, let's start using that notation. That's a 4, sorry. It starts repeating. Probably have noticed that before, but you might not have actually had a reason to take 4 or more derivatives of cosine of x. Well, from here on, it's going to repeat. The 5th derivative, it's going to go back to minus sine x. and has no choice but just to repeat this pattern over and over and over again. That's really nice, because if we do want to get a really high degree polynomial, a high degree Taylor polynomial, there's a pattern to be found. And so we will be able to write down an arbitrarily high degree polynomial in an easy way. That's not always true for any function. It's fairly special. But for our standard library functions, cosine, sine, e to the x, log, there are patterns to be found, and it's really nice. So, for example, let's see, what would the cubic approximation be? Oh yeah, and of course we need the at 0. And of course this story is still interesting and cool if I use a not equal to 0, but just for simplicity and because it's a very natural thing. Okay, double prime. We're going to stay with 0. So it goes 1, 0, minus 1, 0, 1, and then repeats, starting with the 1, in fact. Okay, so interesting thing, the cubic polynomial, the coefficient there has an f triple prime of 0. It happens to be over 3 factorial times stuff, but it's exactly the same. Since that doesn't contribute, the cubic polynomial, if somebody says, I love that quadratic approximation, but I'd like to make it better, I'd like a cubic, I'm willing to go to the complexity of adding a cubic term in exchange for getting a better approximation, you try to add it and you say, you know, the best choice for adding a cubic term is not to add anything. And that is the first hint as to why this approximation is so good. It actually is the cubic as well as the quadratic. So in particular, the error estimate it satisfies is the error estimate for T3. Well, what does that look like? So I'm not going to prove this one, but it's super similar to what we've seen before. It's not really any new ideas. The error estimate for the cubic Taylor polynomial is m over 4 factorial times how far you have gone from the base point to the 4th power if the 4th derivative of x is known to be less than or equal to m on our safety interval, let's say a minus d, a plus d. The only thing that changes is that you're now the error in the cubic approximation that uses up through the 3rd derivative and shares all of its first 3 derivatives with the actual function. The error in that is naturally enough determined by the size of the 4th derivative. If the 4th derivative were 0 everywhere near a, then it would be a cubic, and the cubic approximation would be exact. And so a bound on the 4th derivative tells you how much that 3rd derivative can change away from its base point value. And that's going to give an indication of how far off this cubic polynomial is going to be. And the good news, of course, as long as you stick pretty close to a, then x minus a to the 4th, you're taking a small number to the 4th power. You might get a little bit of advantage here from the fact that that's a 1 over 24, 4 factorial. It might be canceled out in some cases by the fact that the more derivatives you take of a function, the m might get wilder and wilder, and that often happens. But of course, with cosine, the great thing is you can always use m equals 1 for any derivative, and that's really nice. So in particular, here, let me just put it in here, we could just use the quick and dirty version, which is 1 here, and a is 0. And so we would get an estimate that it's about 1/24th of x to the 4th. And that pretty much explains why we got 10 times as much accuracy as we expected to before. Because secretly we were doing the cubic approximation with no extra work. Well, what about the 4th degree? That's where we are going to add something. The 4th degree polynomial, that's going to use this. And so it's going to take the quadratic, which is identical to the cubic here, and then it's going to be plus 1 over 4 factorial times x minus a, of course, in general, but here a is 0. Let me put it up here. X to the 4th over 4 factorial. So that finally, it tells us, okay, now we're really adjusting this and making it better. Adding a cubic was a bad idea. There was no need to do that. But adding a quartic term, a 4th degree term, is going to be a good idea. And the error estimate for that And again, you could be more clever. Well, let me just write down the general form. That's over 5 factorial times x minus a to the 5th. If, of course, now m, it's a little slippery beast. We don't usually decorate it with a sub 4 or a sub 5 or something like that. You could, but it's understood that in this setting, that m is supposed to be an upper bound for the next derivative, the next one that you take after the ones that actually built the polynomial. The next derivative controls the error in this particular kind of error estimate. And again, usually you only have some knowledge of that on some limited region, although for cosine it's particularly nice. This can be used as 1 if you want for any x whatsoever. Same deal, same story. Now you got a 5th power. If this number is particularly small and you're dividing by now 120, both of those factors are going to make this a very small number, guaranteeing without fail that this approximation will be quite good when x is small. So that's a good place to stop this one. It's plenty long. But the next thing is going to be really exciting, which is we're going to really focus on the idea of taking that whole pattern a really long way, maybe even going out to infinity and thinking about limits and infinite sums.